the main theorem we used last time is that if you have a hyperfinite bipartite nowhere to ended graphing that has a measurable fractional perfect matching which is non-integral everywhere, then we also can round it and get a measurable perfect matching. Remind you that in hyperfinite graphings, one always can get a measurable fractional perfect matching in case there exists a perfect matching which may or may not be measurable. This was a very useful application of the Banach-Sachs theorem for us. It turned out that not everybody was 100% familiar with the Banach-Sachs theorem, so for those who aren't, I suggest to check it after this with the guidance of Matt. The Banach-Sachs theorem says, well, one can state it in different forms, but for us, the useful form was that in case we have a probability measure space, or say a sigma finite measure space, the set of edges in our case, and we have a sequence of bounded measurable functions on this, then there will be a subsequence such that the averages of this subsequence converge. So this Cesaro convergence as it appeared a few minutes ago. So we gave a number of applications to this theorem, the amenable version of the Lyons-Mazarov theorem on finding factor of IID perfect matchings in case of amenable groups with bipartite Cayley graphs, unless the group is the semi-direct product of Z, the group of integers, and the finite group of odd size. We, as many in the room, we studied balanced orientations, and also we had some fun with factor of IID processes in the end, Poisson processes in the end. And one of our main motivations was the measurable circle squaring what looks like this, according to the picture drawn by the algorithm of András Máté. So today our main goal is to go into the proof of this theorem and cover at least the interesting part of it. And for this, one useful tool will be what we designed last time, that we call connected toast. So the definition has improved since yesterday, and it got less redundant. And so yesterday it was debatable, but now please believe that this green area is connected. So a connected toast is this one, this system of finite connected sets that not only the sets themselves are connected, but if we take any of them and remove the smaller ones contained by it, then the difference will be connected too. And altogether they cover every edge, or in our case, it will be enough to cover almost every edge. So we know that these exist for one-ended graphings we will work with. But the finite components in the graphings we care about. And we have this middle condition of its three small ones that not only that they are disjoint, these parts, but they cannot be adjacent either unless there is containment between them. So not there is no edge between the two blue blobs, for example, no matter how we imagine the world. So this will be a useful tool for us. And so one of our ways to understand that we will work with the set of measurable fractional perfect matchings. This is the graphing analog of the Edmonds-Polito, where we know that every extreme point is a perfect matching itself, so it is 0, 1 valued. For fractional perfect matchings theory, it can be anything, the 0, 1 interval, and we know that by the Klein-Newman theorem, it will be always the convex hull of extreme points. So we can have, for any fractional measurable perfect matching, we can have a probability measure on the set of extreme points that will integrate to this one. And so the structure of the extreme points, or at least will have this structure what we already could anticipate after the first talk, that an extreme point will assume almost everywhere value 0, 1/2, or 1. And where it's 1/2, that set should be essentially a vertex disjoint union of B infinite paths. We saw some very similar arguments when proving the odd regular case, and we have the same ideas here. So we look at the set of bad edges, meaning the non-integral ones. This is what this likes when searching for a perfect matching. If this contains a cycle or many cycles, then we can take the where are they? We can take these plus minus epsilon circuits, and we can both add and subtract such circuits. When adding it and when subtracting it, we are still in the convex set of measurable fractional perfect matching. So whatever we started with was not an extreme point. So we cannot have cycles. Oops. And in case we don't have cycle, we cannot have vertices of degree 1 either, because the sum of the values at every vertex is 1. So it cannot be that only one of the summands is non-integral if we get an integer in the end. And by hyperfiniteness, almost if we forget about isolated points and we don't have essentially degree 1 vertices, then the rest should have degree at least 2, and the average degree cannot be bigger than 2. So we end up with 2 regular acyclic graphs, which are infinite lines. And then on every line, we have just 2 alternating values coming up. And if this was not 1/2, then we could have a choice of a perfect matching there. So again, other words, the point wouldn't be extreme. It would be between 2 other things. So we have the structure that we have lines where it's 1/2 and the matchings outside. And we are not so happy about the lines, but as we saw in the two-ended case with original rotations, it's inevitable.
So in the odd degree case, could you again just say, oh, by Klein-Milman abstract analysis?
Well, not exactly. I did a discrete Klein-Milman when I only looked at the matchings where the denominator is D, and well, extreme points in the discrete case. So we only had this cycle argument, so such 2 discrete. So if something in this discrete sense was not an extreme point, then it should have also had this structure, and we ended up with the same thing, but the 1/2 line could have been avoided. So it feels a bit strange to speak about to take a convex set. Just take the points with denominator D and speak about extreme points there. But since we added and subtracted only such circuits, with this 1 over plus minus 1 over these circuits, this approach worked. But
so this is also, you have regular degree, like degrees fixed for this person, or no?
I didn't use anything about regular degree. I just removed all the cycles. For some epsilon, I've added this plus minus epsilon circuits, and so then all the cycles were removed at some point.
What I'm saying is that in the previous argument with odd degree, there was, at least in the very end, there was some Borel-Dantelli argument by choosing minus plus 1 over.
Yeah, so that's necessary to stay in the discrete subset, so that everywhere you make only finitely many changes. It's not really necessary here.
Okay, but here you could achieve the Klein-Milman nonsense also algorithmically.
Oh, yes, because you just, on a larger and larger set of edges, you will have integral value, and this will give, so you converge in this sense. The set of edges where the value is non-integral is shrinking, and then in the end, you don't, so for every integral edge, or at some point you will have, yes, that it becomes integral. So yes.
The same Borel Cantelli arguments.
I don't see if Borel Cantelli is really needed.
Yeah, you also need it for the convergence of the matchings. So to get the K over D, you need a Borel Cantelli, but now you can just round cycles and you don't need Borel Cantelli.
Yeah, once you fix it,
just by comparison, if
Yeah.
you take an extreme point. If it has a positive measure of cycles, you distort it, you add epsilon, and there's no randomness. Add epsilon,
Just
and you get a convex combination which contradicts experiment.
yes, but you can make this Kramer here, but I suggest to go on. There will be I'm not sure. I don't think it's needed, the Borel Cantelli, but there. Okay, so using the structure of extreme points, we will have the following plan. So we will work with these measurable and fractional perfect matching, which are extreme points. And so we know their structure, that there are lines we dislike and the rest is a matching. So what we wish is to change it somehow, and in every step to decrease the measure of the bets at the lines. So of course we will use these alternating circuits because, well, we have a limited toolkit and Kramer, and we will use connected toasts. We will see soon how to find cycles. And luckily for you today, I don't go into the case when we need some other matching arguments. It's a pain. But we will concentrate on the case when this fractional perfect matching is separated away from zero, so it's greater than some epsilon naught. This sounds like a very special case, but after understanding it, you would rather be surprised that it doesn't cover essentially every case. We were surprised ourselves finding it out after months, but so I concentrate on this, and there will be some hand waving by this covers most of the interesting cases. It definitely covers the case of regular graphings. So this will be the name of the game. But so for quite a while, I concentrate on this case separated away from zero. This also means that our graphing will not only be locally finite, but bounded degree. It's the degree is at most 1 over epsilon naught.
Okay, so the parenthetical random there that you're sneaking in sounded so.
Oh, thank you. So we also prove, of course, that, or not so surprisingly, that the fractional perfect matching we start with is a convex combination of perfect matchings. So there is a probability measure on them that it integrates to this one. And in this such proofs, one always can think of 2 ways, depending on education, heritage, whatever, that if you want to have, say, a martingale, or always take with you a measure on perfect or fractional perfect matching, or rather you prefer in everything, you only go for existence, and in every simple step, you decide what you do to improve some potential. In case of this proof, most of the time the later works for those who prefer it. It was less the case in the odd case. But sometimes it takes a long time for us when we improve a matching, but it won't be an extreme point, and then we need to round it using Krein-Milman and this. So in the middle of the story for a while, we will rather have a measure on fractional perfect matchings, though it will be a finitely supported measure. Okay, so let's get into the one-handed case. So the lemma what we will use here is this one that, so we have this set of lines with positive measure, And our goal is, it's not apparently clear why this is good for us, so one might have educated guesses. Our goal is to find a set of cycles, and the set of cycle or k disjoint families of edge disjoint cycles, so tons of cycles in other words, that every edge not on these lines will be covered by at most one of these cycles, and at least half of the edges on the line will be covered by quite many cycles, say at least k of them for a k chosen by us. So somehow, of course, our plan is that again, we turn these cycles into circuits, we add and subtract then epsilons on these edges when time comes, and then on the line we will go far from 1/2, elsewhere we don't change it too much, and when we use it rounding Riemann, we hope that we see a nicer extreme point. So at least I hope the philosophy is clear. So our point is finding such a system of cycles that cover those things on the lines many times and the rest a very small number of times. And it's not, at least not hard to prove by picture how these look like before we give a real proof. So we imagine that.
Can I ask? Maybe I didn't digest it correctly, but for smaller k existence, doesn't imply the existence of larger k?
You want these sets of cycles to be disjoint.
They could be empty though.
But you want it for a large case. So you want to cover the edges on the line, many of them, many times.
You want to do it many times. So,
yes, okay. So when you add and subtract these circuits, then that's something you get far away. So these lines will be quite destroyed. But of course, you will get it elsewhere, and the hope is that since every other edge is in only one cycle, you won't regret it that much.
Okay, follow now. Thank you.
So that's the.
Could you quickly explain this picture again?
I prefer to explain the next one, which is not so different, but we can return to it. But
with the statement of the dilemma.
Okay, so. Oh. Yes, the captain leaves the ship. It's not a good sign. So in our case, we assume that half of the edges are in these four lines. That's maybe not so intuitive. And k is equal to 2. So inside this circle piece of toast, we will then find one system of cycles, the two green cycles, the other one is the four red cycles, and they will cover these parts inside the very small cycles twice. And since they are in different pieces of the toast, everything else not on the lines will be covered at most once. So that's what we wish to see, and we will be more precise about it. But formally, that's the statement, what you are looking for. So edges on the line, most of them will be covered many times, outside the line, only once.
Where in the statement you have that those cycles somehow are in separate parts of the toast?
I don't have it in the statement, I have it in the proof. That's why we develop the toast, that we can then work in different pieces of the toast. So, I mean, once we worked so much with them, let's use them. Okay, so this is the proof by picture, and the proof by proof is maybe not so much fun to read, but I'm not great at drawing pictures in this. So the board is the bigger piece of toast. We have a number of smaller pieces, say these three. And we have our line, so it comes inside the toast and leaves, and comes and leaves. And let's have a third one. So these are the lines. And what we do, so we know that the complement of this three is connected. We look at the set of vertices, so which are just adjacent to something in this smaller piece of toast. So this set will be red, and I denote it by something. Oh, sorry, please believe this trivial lemma to me. It's by induction on the size of S at some point. So we have these sets of points, which are the red points, and adjacent to something in the smaller piece of toast, but only once, not twice. I have chosen these pieces that most of the lines, so the lines inside these white pieces are at least half of the line altogether. So this notation M1 and so on is just refers to the hierarchy of these smaller and bigger pieces. So we are at a large piece where most of the line is covered. And once we have this point, we use that this is connected. And so this is an even set of points, if I drew the picture well. So we connect them somehow in a way that, so we add this blue set of edges that outside these pieces, every vertex will have in this blue graph even degree, but the red vertices, which are the exit points. And then, yes, so then we can just add these inside. How complicated picture. So we added what's inside these things, and we have ended up at a graph where every vertex has even degree, so it can be decomposed due to Euler into a disjoint union of cycles, and this will be our set of cycles. And we do this in so they are not vertex disjoint, but luckily we won't need that. We only care about the edges this time.
Also, that one vertex should be wrong, yes?
Yes, so this
that one, no?
That
yeah, red.
Oh no, because it has two neighbors. Well, it's not red because it has the parity. It has two neighbors, and yes. This is a nasty detail, but yeah, that's why it's not red. And so is this not red, but remained yellow. So we want the parity to be fine. So this is what we do in every piece. And so whatever is inside was covered, and moreover, we also cover this. Okay. So any questions to this proof? Oh, then remain silent forever. Oh, well, what was the lemma? So this was the lemma, and it's a nice exercise to check this for two-ended graphings in case every component contains at least two lines. To find this, it's a good practice to make friends with these cycles. So we have this, and then. Okay, so our plan is just to add the alternating circuits everywhere, but before adding it, we want to make sure that it's a measurable fractional perfect matching what we get. And since the value is now in this extreme point 0 and 1 at many places, adding plus minus epsilon will lead us out of the 0-1 interval. So this is the point when we use that there is a fractional perfect matching, what at least epsilon 0 and at most 1 minus epsilon 0 everywhere. This one denoted by tau, and we simply take the the convex combination of these two fractional perfect matchings, and the epsilon that will be the measure of change for us will be lambda epsilon naught for later records. So we just took a convex combination for safety issues before the real action starts. So the other part is to imagine we have no idea how to choose this cycle. For every cycle, we have two possibilities to choose an alternating plus minus epsilon circuit. We have no idea what's the right choice, so we do it randomly, independently, with probability half-half, and we get a distorted matching this way. So we add this random story, so psi I, or it are the circuits, and then we will just sum them up with some random coefficient Zi from plus minus 1. So luckily this randomized fractional perfect matching will only use this finite amount of randomness. Finite amount because we may assume that altogether there is a bound on the length on these cycles, and we can use Crookes theorem. But of course, yeah. So sorry, that's why we can make this disjoint. Okay, so this is our candidate for an improved measurable fractional perfect matching, and well, we need some calculation to see that it will be really an improvement. Wait. Sorry. Yeah. Okay. Yeah. So this lemma I forgotten to explain, but maybe it was better to leave it to a later point. So working with measurable fractional perfect matchings, if it's an extreme point, then this formula here exactly tells us. So this is designed just to measure. This is just the measure of these lines, what we dislike with half. So this, believe me, that for 0 and 1, this will be 0 if we substitute it for psi of E, and for 1/2, we will get 1 here. And so I mean,
is your previous set of lines?
Yes, so we have a phi, a configuration phi, which is an extreme point, and we will find another one psi, where which has a smaller set of lines. And just in order to estimate the set of lines, we will use this formula. So if, well, for an extreme point, believe me that it's really the set of lines. If we take this 0, 1/2, 1 value, then it will be okay. And apart from this, it's a oh, yes. Sorry. So L of pi and L of psi are the set of lines for an extreme point. And so luckily for us, this is a concave function. Well, it's a negative of a convex function to integrate. This means that whenever we will have a non-extreme point, so a measurable fractional perfect matching, and we apply Krein-Milman to it, then we will have and we get extreme points, then we will have the right inequality by Jensen. So, well, the price is that we have to carry this one with us, but it could be much worse. Okay, so this is the plan to. And so we did the. Yes, that's. So first we make this convex combination, and then we start to we find this set of cycles by this covering lemma, and we add the corresponding plus minus epsilon circuits where we choose randomly plus or minus from the two options. And we end up then this random sum plus the convex combination. And so we will make the basic calculations showing that this works. Any questions to this?
So the original match
won't be horrible, I think, but still, this is a point.
Yeah.
Where to?
Right, so let's make sure it's cool.
Okay. Okay. So the point for us will be that, well, when we make the calculations, then the dominating term in this story will be the one which corresponds to the random sum. And this will be in expected value, the root of k times epsilon times the measure of the line. So that's what we are aiming for, that there will be improvement because we have this main term and the others will be easy to bound. So for this, we should choose k of greater than this one. Just in the end, when we compare the constants, sorry, it's a bit dense here. Yeah.
Why do you need various?
Oh, we don't need it. It's just okay. Yeah,
You don't need
yeah,
any
you
central.
I suggest not to discuss it. I admit that this is shooting for the pigeon with a cannon, shooting the pigeon with a cannon said in Hungarian. There are a few simpler ways to do it, but somebody absent loves to use various and it's so good to blame somebody absent. But it's a quite inconvenient thing to have such a statement that everybody knows, but it's not so easy to refer to. But in any case, let's concentrate on the proof. So, we have these nice differences. Rho of z is the new one. Pi is what will be for a good choice, the new fractional perfect matching, and phi is the old one. And luckily, the 1/2 disappear, and so we have this nice difference. And so our point will be that it will be dominated by this random part, which is only on that part of the integral which is on the lines. But so where outside the line, it's quite easy to estimate it because we have added only at most epsilon when adding the cycles to it. And when we took this convex combination with coefficient lambda for the original tau and 1 minus lambda for the actual tau, our loss will be at most lambda. So we have this bound epsilon plus lambda everywhere outside the line. And this will be good enough for us. And by the way, in order of magnitude, epsilon is smaller than lambda, so we can think of it as a lambda. On the line, being on the line means that phi of p is 1/2, so this formula simplifies to that one. And so that will be the random sum we like minus a lambda half. So modulo some lambda, we really have what we need. And so we have chosen, what was k? Where is k? Oh, where are you? Let me know if you can see k. Oh, yes, it's over there. So we need the choice of, so k should be just chosen that when adding to these edges where the value was 1/2, we add, we modify them with this lambda and where lambda is built in here and so on, then you get something, and it's well not hard to see that this can be satisfied. Only besides epsilon and lambda, everything is a constant, and we need k to be less than something over lambda, and root of k much greater than something lambda over epsilon. So we can choose this lambda and epsilon to satisfy this. Oh, maybe. So it's not a very sophisticated choice. Okay. So we have this improvement. So in the limit, we just, whenever we have a, oh, that's nice. Yeah, this goodbye symphony. So we have this measurable fractional perfect matching, and we find always a new one that the measure decreases. And we need to, that's a good sign. We need to be a tiny bit careful that the limit exists. Here we have again choice if we want to somehow have some extra rules to finish this process in omega steps, or we let it on, and anyway in every step this measure increases, so at some countable ordinal we stop. Let me choose the later strategy. So we need for these countable limit ordinals that the limit exists, but from these estimates what we did, it's quite clear that most of the changes will be on the line where it was originally 1/2. So the improvement times a constant will be an upper bounding on the change in total, say. That will be the change where we change from 0 to 1/2 or 1, or so between these values will be at most 3 times the improvement, how the size of this 1/2 line decreases, because this improvement was really in the main term in these calculations, which just involved all the changes. Okay, so in the end we can define it from limit ordinals, it decreases, so as for some countable ordinal we will stop and we have our measurable perfect matching. So happy end. Any questions? I don't insist on it, but okay.
So
Matt will be also happy to explain.
yeah, I was just gonna ask, so, and I think you probably already addressed this, but you're saying that, I mean, there's an extra argument to say that Borel can't tell you applies here.
Yeah, so not so extra, because when the main term is on the line, and on the line almost we have improvement, then it means that really the other change. So in every step, so you look at how many times the value will change on a edge, you sum this up for all these ordinals, and then this sum will be at most, say, 3 times the improvement in the measure, so it will be a quite visible finite bound. Simply it's so much dominated by this random main term. Okay, so this has covered the case when we are separated away from 0. Of course, we really only use that on the cycles we use. We are separated away from 0 and 1. So in case we just face the general case, we try to choose this epsilon 0 to be small, to have something one-ended in the component. So we have a number of lines in a component. We choose epsilon 0 small enough that these edges where the value is between epsilon 0 and 1 minus epsilon 0 connect many of them. In case there are, in case we get components where infinitely many lines are disjoints, these should be one-ended components, and we can apply what we did, because superlinearity is equivalent to one-endedness. And in case we have finitely many, but more than one of them, then it's really an exercise to think about it, that this will work out. And we were quite unhappy finding out after a while that in case there is only one line in a graphing, then we need another argument. And this takes quite a few more pages, though it's so easy, so that made our paper somewhat longer. But this is essentially, this is only the only case what's essentially not covered by this argument. It's of course a possibility. In that case, one somehow tries to find augmenting paths which somehow jump over a long subsegment of the line, but I shouldn't speak about it. That's for another day. Okay, so we were at the end of the proof. And maybe let's just mention some alternative history, that if we don't look at the hyperfinite world, but matchings with bipartite matchings with expansion, then we basically know that we have always, or we know that we have always perfect matching. here expansion means that if we choose this set S in the first line from one class of the bipartition, and it has a size at most half of this, then its neighborhood will be large. So it's a measurable whole condition. So if we have this, then we will have perfect matching. This includes the case of Kazhdan groups, for example, when it's an ergodic action. And first, this idea, or well, a different form of it, was used by Margulis to solve the Bonner-Hruziewicz problem in larger dimension. If there is any S1 invariant finitely additive probability measure on the Lebesgue set of the sphere, and then because this is a Kazhdan group in that case, I hope I chose the right answer here amongst so many experts. And for smaller dimension, it turns out later that even though the group itself as abstract group is not Kazhdan, the action is still mixing well enough. So, and in one dimension, it's not true. And the, say, discrete or countable graph theoretical counterpart of this was the Lyons-Nazarov theorem that bipartite Cayley graphs admit vector phi ID perfect matchings. In a higher dimension than 2, it's still an interesting question. When are two bounded measurable sets equidecomposable? And Gabor Lukashvili, Rashmati, and Oleg Kurko proved this in case of sets of non-empty interior and equal measure. So more or less the picture is that the case with expansion is well understood. I think we can slowly say that the hyperfinite case is well understood, but everything else is left out, essentially. But there are some basic examples, most of them being hyperfinite. So the Lackovich example by modification by Clinton, Conley, and Alekos Kefris, and Marx proved this for the Borel graphs. I proved it in the measurable case that certain bipartite deregular trees don't have a measurable perfect matchings, even though it's quite hard. They are quite non-amenable in the graph or treeing sense. So I wish to tell you the proof of this later one. So of course we so this example will be a measurably bipartite regular graph, deregular graph, that every bounded circulation is almost everywhere 0. A circulation of yes is a flow that sums to 0 at every vertex in the graph theoretical language. And so knowing that every circulation, say bounded circulation is 0, means that there is no measurable perfect matching, because if there was a perfect matching in a bipartite graph, then we could say that, say, we send from one class to the other d-1 on the matching edges, and in the other direction we send 1 on the non-matching edges, and this would sum to 0 at every vertex. So circulations will luckily encode matching for us, but also different things like, so we cannot have a regular subgraph in the same way. We cannot have it as a disjoint union of infinite lines, that a vertex disjoint union of infinite lines that cover every vertex once. So we cannot have such a partition in case our regular graph has no circulation or graphing. So we are going to construct such a graphing without non-zero circulation. Yes. So we will rely on one basic fact, that if we take a, say, absolutely integrable circulation and a bounded function from the set of vertices to the real line, then the integral of the circulation times the gradient of this function, the difference on edges, will be 0. That's again a good exercise for those who haven't seen it yet. Of course, both a circulation and this difference is an anti-symmetric function, so it's not hard to define this integral, no matter from which side we look at it. So we will rely on this basic fact because it's very nice. So in case a function is not a circulation, there will be another function simply that proves this such a bounded function P. And our strategy will be just a diagonalization method where in every step we make sure that for every candidate circulation we will have a function in a kind of inverse limit of finite graphs that makes sure that we won't have any real circulation in the limit.
So it is like the rho was F, right?
P.
Z.
Yeah, that can easily happen, but oh yes, but so locally, okay. Sorry, I did not expect to get so far. Yes, so P and F are interchangeable. So this is not the most beautiful slide possibly, but it's the message is quite clear, or I hope it will be very soon clear. So we will have a sequence of finite graphs, starting with the complete one on D plus D vertices, complete bipartite one on D plus D vertices. And what we want is that we will get essentially, we want somehow to rule out every orientations of these finite graphs in the next step. So whenever we have a graph Gn and we want to define Gn plus 1, we want to do it in a way that Gn plus 1 will be essentially a cover of Gn. And for every orientation, so if we wish plus minus 1 valued circulation, there will be a function on Gn plus 1, which will be essentially the difference of this circulation for most of the points. So for this function, this basic formula will clearly not hold. And in the limit, this function will be the witness that there cannot be any circulation close to that one. So the natural choice is, if we just want to take care of one single orientation, is to take the topological cover with automorphism Z in the covering group. And well, we think of the graph as a simplex, of course, and then we take the mapping to the group of integers that's induced by this circulation. So this will be an infinite cover. And so the elements of this will be just pairs, one from the original graph, and the other will be one element in the group of integers. And so then there will be a function present, which is whose gradient will be exactly the lift of this orientation. But we need this for all orientations, so we will have a large product. So the ideal candidate would be for this cover that we have this that corresponds to the automorphism, a high power of Z, the group of integers, to the number of orientations. And since we should make it finite, we want a sequence of finite graphs, we just chop it off and take a big box of this infinite graph. And this is almost regular, and we need it to be regular, but it's not regular on the boundary. If we forget now about measurable bipartiteness, we deal about circulations only for the sake of simplicity, then we take 2 copies of this, and for every vertex which has degree less than the D, we connect it with its twin as many times as needed, and so we end up at a regular graph, and we continue in this fashion. So in every step, we make sure that for every orientation, when we make the lift, there will be a function whose gradient will be essentially this the lift of this orientation, and at the vertices where this is not true, the difference will be 0 on these edges, so it won't be too high. We can use the basic fact there. And so once we make it, we look at the limit, the inverse limit of this. Well, at least on the set of vertices, it will be a real inverse limit. And so we will, from this, and simply we take a potential circulation for the sake of contradiction, which is absolutely integrable. And we can approximate it, its sign by an orientation for one of these finite graphs. And then, this will be in Gn, the nth graph in this sequence. And then on Gn plus 1, there will be a function p, which just maps to this finite segment of the integers, and that will be whose gradient will be essentially this orientation Cn, and then C times this should be 0, this integral, the C times this difference, but it should be, on the other hand, very close to if we just replace C by Cn, because P, the difference of P will be small on every edge. It can be plus minus 1 or 0 in our construction, and that would be, since that's the sign of C of n, just the L1 norm of Cn, and that would be a contradiction for us. So that's a construction of a regular graphing without any circulation. And in fact, it's not hard to see that we can also find a free group action on it. Well, it will be just the free product of two element groups, but at least it's a Schreier graphing of a free action. So in every step, we can make sure that whenever we connect twins, every twin will have the same deficiency, so they will miss the same group elements, so it won't be hard to connect them. And we need to change this construction a tiny bit in case we want a measurably bipartite construction. So in that case, instead of taking two copies of the original and just connecting twins, we take d copies, and for every vertex with a deficit, we add as many vertices as the deficit and connect this to the siblings of this one. So we make sure that they stay in the same class of the bipartition after the lift. So the preimage of a vertex or these copies will be in the same class of the bipartition. Any questions to?
So you said that without the bipartition, you can witness it as a free action of
yes, without the bipartition, you can have this free product if you wish it. We can call it edge coloring in this case. And so in every step, when we take this big thing, we can just lift the action or edge color, and where we have some deficit on the side, we will have the same deficit for twins, so we won't have any problem how to make it consistent.
Once it's bipartite, you have no chance.
Okay.
Because that one will have no perfect matching, and if it carries that, right?
Right, sure.
If it has the action of
the
free product, then it would have perfect matching.
Right.
And the point is to not have.
So we also modify this construction with LATSI to construct a number of funny things like a tree that has exactly one balanced orientation, measurable balanced orientation. There is quite some freedom in this construction when looking at the subspace of circulations. So it can be used for a few funny things. If no more questions, then thank you.
Yeah, any questions? All right, if not, let's thank Gabor again.
Either make a drop over the speakers and the younger more genius, as I would say. Okay, I would like to thank all of the speakers and the TAs for their incredible work and amazing lectures this week.
Okay. Thanks for the organization that made it easily possible.
So we'll give a full 10-minute break and then we'll come back for the last TA.